So new topic, so we're okay with radonicotium. Actually, it is a new topic, but it's, you'll see similarities. There's a pedagogical reason to cover one and then the other. Let's talk about rectifiability. So if we have a curve, so given a curve, gamma, so this is a parametrized curve in, let's just say R2. You can think of this as the complex numbers, if you like. So what I mean by that is, so I have a function z from a, b to either R2. So let's just write it as R2, but so z of t I'll think of as x of t comma y of t, or I'll think of it as x of t plus I y of t. X and t are real and continuous. So being a curve is that it's continuous. Okay, so I mean, here's a curve. Here's z of a. Doesn't have to be nice. Doesn't have to be simple. Z of b.
Choose a space-filling curve.
For example, that's the issue that we're trying to deal with. Can we compute length? When does length exist? Okay? That's exactly the issue. So definition, the length of gamma. Well, how do you want to measure length? If gamma was continuously differentiable, then it would be nice. So maybe, well, pre-length or something. So aside, if z is continuously differentiable, you could define the length as the integral from a to b, right? The slope, infinitesimal slope. So that's x dot squared plus y dot squared square rooted. Okay, little bits of arc length, that is the arc length integral. That would be nice. A, I never said it was differentiable, so x dot doesn't have to exist. Can we have a more general notion of length? Well, let's approximate this notion by rectifying the curve, chopping it up into straight segments. So what we'll do is we'll take a partition, so P is I'll write P containing A and B, a partition. Partition, I mean, I start with T0, then I have a strictly larger T1, all the way up to some number, which is not specified, some finite list of T's that decompose A to B. And then we can look at the sum over the partition of z of tj minus z of tj minus 1, and just take that absolute length. Okay, so that sum, it's like, so here's T1, and here's T2, and T3, and T4, and so on, and then you straighten the curve out into straight lines. Okay, and the length is the soup over all partitions of this thing, if it exists.
So we're infinite, that's when we say it's not rectifiable?
That's right. So definition, gamma is rectifiable if its length in this definition is finite. Okay? Or if there's another way of saying this is if there's a universal constant, so that for any partition this thing is bounded by that constant. If it exists, well then you can take the least of those constants. That'll be the soup over all partitions. Okay? So that's rectifiability. This is our notion of length. Now let's talk about, so this was in the case of a continuous curve, but for a general function, it's funny because the same notions have lots of different terms attached to them. So in the language of curves and rectifiability, this is the length and the notion of rectifiability. For a general, not necessarily continuous f, again, let's say from A to B, from A, B to C, we'll say it has, we'll say its variation of f relative to a partition of AB is exactly this thing. So it's a sum over the partition, f at tj minus f at tj minus 1 with absolute values. Can you read that, or should I rewrite it? Rewrite it?
What is we see R?
So variation over the partition of the function is, let's just write it explicitly, a sum as j goes from 1 to n, absolute value ftj minus ftj minus 1. And let's see if I got the bounds right. The last one is n, the first one is 0.
And you can define this into any metric space.
You can define this into any metric space, exactly. This makes complete sense as long as you have a metric. Okay, the distance between these two things. That's right. Okay, so that is the variation given a partition, and definition. F is of bounded variation if the variation for any partition is bounded. If the total variation which is the soup, so let's give this a name. Do I have a good name for it? Let's just make it T. T of F, which is the soup over all partitions of the variance, or the variation, not variance, is, so this is the total variation, and F is of bounded variation if this is finite. So in the case of F is a curve, F is the graph of a curve, the word total variation is what we called length, and bounded variation is what we called rectifiability. Does that make sense?
And so in other words, like this just coincides with the
Completely
previous-
coincides.
Okay.
Yes. So if F is a curve, then total variation is length, and bounded variation is rectifiable. These concepts obviously grew up not talking to each other until a little bit later. These words became ingrained. Okay, let's prove a little lemma. So a curve, a parametrized curve gamma given by z of t is equal to x of t, y of t is rectifiable if and only if the components are of bounded variation. X of t and y of t are bounded variation. And the proof is one line. Well, let me leave everything but this little observation as an exercise. This is the triangle inequality. And this is some very weak Cauchy-Schwarz. Or just, it's a square. Squares are positive. So the values of squares are positive. So I'll let you argue these two things and then decide that rectifiability happens if and only if each of these are a bounded variation.
So for the second thing, square both sides and see what happens?
Yes. Okay? All right. Examples. Let's talk about some examples. So the simplest example which will, as often happens, the simplest examples are the prototypical ones. So here's an example. F is monotonic. F is, let's say, increasing. So if F is increasing, then for any partition, what is the variation? Bless you. It's a sum from 1 to n of absolute value f of tj minus f of tj minus 1. But it's increasing, so you don't need the absolute values. And it telescopes, so it picks up the last minus the first. And it's the same overall partition, so it's the soup also. Okay? That's kind of an easy example. And of course, this is finite, if f is finite. I didn't say continuous, by the way. Just f is increasing. Okay, example 2. Example 2. If f prime exists for all x in AB, and f prime is bounded, then f is of bounded variation. Why is that? Mean value theorem, exactly. Proof? Mean value theorem tells us that if I have f of tj minus f of tj minus 1, that's equal to f prime at some in-between point, at some in-between, what's that? Cj, sure, times tj minus 1. So in absolute value, this is bounded. This thing is bounded by, well, I assumed f prime is bounded, so let m be the bound. And then if I want to add these guys up, so the sum, so the variation along any partition is bounded by m times the length, since this is now a monotonic function. Okay. Example 3. Let's make things a little interesting.
Move the page up a little bit.
Yes. Let's see. We have example 1 and example 2. This is going to fall. There it goes. Thanks. This is a fun one. You guys thought about this curve?
Is it a non-example?
It's a non-example. It's the topologist's sine curve. So think about what happens. So at 1, we have sine of 1. I don't know what that is. Something. 1 is pi over 3.
Yeah.
Okay. And then it does sine forwards. The infinitude of sine, it does from 0 to 1. From 1 to 0, backwards. So it's going to go. And then it has no value at 0, so let's make it equal to 0. So it's continuous.
Except at 0.
Even at 0, because what does it mean to be discontinuous? Is that there's a subset of connected is the term I'm looking for, not continuous. Connected. Yes. This graph is connected. So this graph is connected. Cannot be the disjoint union of two open sets. Is not contained in the disjoint union of two open sets. And yet it's not path connected. Because give me a path that gets from 0 to any place. Okay? Not path connected. Not path connected. Okay? The length, well, it's going to traverse minus 1 to 1 infinitely often. The length is infinite. So it's obviously of unbounded variation. Let's make this not of bounded variation, but f prime exists everywhere.
So, wait,
Almost everywhere.
real quick though, what's the sketch that it's connected again? So like I take two open sets, one of them has to contain 0 or something, and then what happens?
Yeah, exactly. I have an open set that contains 0.
Okay.
If it contains 0 and it's open,
Yeah.
then it contains some interval to the left of 0.
Right.
But for any interval,
Yeah, some portion of that.
we're totally nice and connected
Okay.
except at 0.
I see.
And the fact that we're taking it open means we have room. So anything that covers this part can't also cover the rest without breaking the continuity of the original curve.
You can keep even like adding points to like the vertical.
Yeah, you could take
segment.
the entire minus 1, 1 interval.
Yeah.
Or so
Any-
just put
any
put anything
subset,
there.
your Cantor set, your favorite. Subset of minus
Vitalik
1.
set.
Any connected set.
Any set, right? Any set in minus 1, 1.
Any set in minus 1, 1, yes.
Yeah.
And it will be connected. That's it. That's as a subset of the plane. I want to think of it as a function, so I just want it to have one value. So give it any value between minus 1, 1, such as 0. So the derivative can exist without the function being of bounded variation. The converse is what is our big theorem of the is it the converse? That the converse is true. This is false. Derivative existing almost everywhere does not imply bounded variation. Bounded variation does imply derivative existing almost everywhere. That's what we're building towards. So building towards f prime bounded variation implies f prime exists almost everywhere. Okay, there'll be a nice homework on what happens to these functions. So maybe let's call these examples 3 prime or 4. What happens to this? Let's take sine of 1 over x to some power, and let's give it a little help to some other power, and 0. If x is 0, and
then A and B are just like any real numbers?
yeah.
And that's continuous for certain A, B, right? Like A greater than 1 or something.
Well, if you think about the graph of x to the a, even if a is like 0.1, it's like the graph of square root. And sine is from minus 1, 1. So actually, whatever this graph is doing, it's doing this. The question is who wins? How quickly this is oscillating, or how quickly this is getting pinched down to 0. So there are ranges of a and b, and the homework is to work out those ranges where this is or isn't of bounded variation. So now you only have one option for who you're going to put here. But the question is, so for which pairs A and B in the positive reals is
Sorry, R2 squared? Just the upper quadrant, open upper quadrant is or what?
yeah, the open first quadrant.
Okay, thank you.
You want me to put parentheses? It is f of bounded variation. Okay, so what the reason it was obviously not a bounded variation is because or finite length, is because it traverses minus 1, 1. Now it doesn't traverse minus 1, 1. The amount that it traverses is getting smaller and smaller, but how often does it traverse that amount? Depending on the speed of that b. Okay. So those are some kind of examples. We discussed total variation. let's talk about real valued functions. So if f is from AB to R, then we can speak of the positive variation and the negative variation. Let the positive variation PF be the sup over all partitions f of tj minus f. Run out of room. The positive variation is a sup. I need to do something so that this doesn't fall down. Let's do that. That's better. Yes. Why didn't I think of that before? We have like 5 lectures left. Okay, the sup over all partitions of a sum f of tj minus f of tj minus 1. That minus 1 is in the subscript, believe it or not. Only over those intervals on which I don't need absolute values and this is positive. In other words, the max of this in 0. So if from tj to tj minus 1 the function went down, don't add anything. Okay? So this is the positive variation. And similarly, there's a negative variation. And negative variation, which is the same thing, the sup over all partitions, the sum where this thing would be negative, but now I'm going to take the minus sign here.
So that, yeah, so it's positive.
So that this thing is positive. Okay, does that make sense? So the positive variation, the negative variation, and now let's do something a little bit, let's restrict a little bit more involved. It's not that much more involved. For x between a and b, write pf of a to x for and the same to be the supremum, the same supremum over all partitions, not of the entire thing, but just of a to x. In other words, don't of the same quantity. So I'm just restricting. I just want to know what's the positive or negative variation, but only on a piece of the function. Okay, so the function restricted to this interval, and same with negative. Same for the negative variation, and same for the total variation. Total variation.
Which is positive plus negative.
That's the theorem. So as defined, it's just this thing, but with absolute values.
Yeah.
But I guess it's obvious that it's positive plus negative because that's what it is for every version. Well, there's something to prove. Let's prove a Jordan type decomposition. So lemma, and this should remind you of the Jordan decomposition of sign measures. So if f from a, b to r is of bounded variation, then for all x in a to b, first of all, f of x minus f of a is equal to the positive variation from a to x minus the negative variation from a to x. And second of all, the total variation from a to x is the positive variation plus the negative variation.
This is like, is this assuming that they exist? Like these, what if like both are infinite?
I have to prove that they exist. The assumption is that f is of bounded variation.
Oh, okay, and then given, okay.
Okay.
Can you say again what is the name of the lemma?
It has no name. I'm just saying this should remind you of. This should remind you of the Jordan decomposition for sine measures.
Oh, so what does ALA mean? ALA.
Allah. Oh, it's to remind you of. Allah is like as reference to,
Oh, thank you.
as happened in this other, in analogy with.
What is it? It's French, right? or something?
It's French.
Okay.
As in.
And
I think there's
I feel like 2 is true whether or not we assume f is a bounded variation if we allow extended equality.
Values. Yeah.
You could have like infinity minus infinity or something, right?
2
Well,
has
with a plus.
2 has a
So both of these are non-negative. So.
Yes, yes.
Yes. Okay. How are we going to prove this? I mean, hopefully you see kind of where this is headed, because this kind of looks like a fundamental theorem of calculus thing, and we're going to add up a bunch of stuff with a partition. So we're building up the.
integral.
We're building up towards that. I mean, that's the real. I said we're building towards, if it's a bounded variation, then the derivative exists almost everywhere. And then if you integrate that derivative, you get back to f of b minus f of a. That's what we're trying to get to. Yes?
Can you go up to the negative variation? Yeah, the NF. Oh, okay, so the whole thing is greater than 0. I thought that you just said the part inside is greater than 0.
Well, the part inside is greater than 0, and you're adding a bunch of
Yes.
such.
Are we gonna assume from now on that we're doing functions from R to R?
Unless otherwise specified. But yes, we're trying to build up to the fundamental theorem of calculus on R. And then you do the complex ones by taking real parts and imaginary parts. Okay. Let's just prove this. This is not hard. It's one of these things that's intuitively very clear. So what do you do? Well, what is P? It's the supremum of all the partitions of a to x of the positive parts. So that means there exists, so since P, not P, this P, PF is supremum, there must exist a partition of a to x such that if you add up the plus parts of the partition, f of tj minus f of tj minus 1, you get within, so this minus pf on a to x is less than epsilon. That's what it means to be a supremum. There is a partition that gets within it. And in fact, from one direction, from above or below, whichever way it's supposed to go. Okay? And same with the negative. Same with nf on a to x for some other partition, for a partition p prime. Some other partition.
Take the common.
Take the common refinement.
Yeah.
Take p twiddle, common refinement. Does everybody know what I mean by that? If this is A to B, and here's one partition, and here's another partition, just take all of them. Okay? So if this is the one partition, is the other partition, just take everywhere where there's a check, that's your new partition. And an easy observation is that if p twiddle is a refinement of p, of P, then I guess I don't have a notion of I do have a notion of variation. So the positive variation for that partition of F on the refinement can only increase the positive variation of the original.
It's like triangle inequality.
It's triangle inequality. It's literally triangle inequality. Okay? So then you're basically done, because if these two things align, so you have a common partition that gets within epsilon of the plus part and the minus part, but if you add those two things up, but for P tilde, this common refinement of both the thing that gets within epsilon of the positive part and the thing that gets within epsilon of the negative part, if you look at the sum over the plus part of f of tj, let's see, how do I do this? I'll go like that. Minus f of tj minus 1, that's going to be very close to the plus part, and you subtract off the sum over the minus part of minus f of tj minus f of tj minus 1.
So we're now using tj's as the elements of p twiddle,
P twiddle.
And of p above. But we're kind of renaming them.
The tj's are generic elements of a partition. So given a partition,
Whichever partition
we're referring to.
We can replace this for the absolute value.
Exactly, but what is this? This is the absolute value. Or not even this is the absolute value, just notice there's a minus and these are finite sums. So then it telescopes. This is equal to f of x minus f of a.
What is the meaning of P times P variance, P?
What I mean is this expression, wherever it is, this expression I'll call the P variance of the partition, the positive variance given that partition of that function. Okay? So those expressions only increase when you refine. And so for any partition, this thing completely telescopes, because minus, these turn into pluses. And now you're just adding the values of the function. So that telescopes, and that telescoping sum is within, and this is within, let's say, 2 epsilon of the positive variation minus the negative variation. And so is this. Okay? So that proves that f of x minus a, f of x minus f of a is the difference of the positive and negative variations. Are we happy with this? What do you do for the total variation?
Change that minus sign to a plus.
Change that minus sign to a plus. I can do it here. For the total variation of f on a to x, this is a plus sign. And then you observe that that's the same thing as taking absolute values. So this is absolute value, this is absolute value, that's what the total variation is supposed to do.
What were you trying to prove again? What was our
The lemma, let's go back to the lemma. If you have a function of bounded variation, then the positive variation minus the negative variation recovers the difference of the values, and the total variation is the sum of the positive variations and negative
We just
variations.
showed it goes epsilon, 2 epsilon close.
Yep. So this is within epsilon of that expression. This is within epsilon of the other expression. The difference of those expressions for any partition, because it telescopes, is the endpoints. And so this thing approaches this value.
So our function is a difference of two monotonic functions.
That's the next lemma. That is the next lemma.
That's this lemma, right? In a sense.
That's this lemma, which I will state now as a theorem. So theorem, let's say it like this: f from a to b, from ab to r, is of bounded variation if and only if f is the difference of increasing bounded functions. Increasing bounded. Okay? The proof in this direction, if f is the difference of increasing bounded functions, well, its total variation is not more than the sum of the variations of the functions that made it up, and they're increasing, so they're bounded, so they're variations, telescope. So this is obvious. The proof in the other direction,
F1 is PF, F2 is NF.
PF, so let's be a little careful. F1 of x is PF on AX plus F of A,
That's a good point. Yeah.
and then F2 of x is negative variation on A to x. And these are increasing and bounded because they're bounded by the total variation. And the total variation is finite. Yeah, so you don't like something.
Why is the F2 the NF?
I'm trying to show that a function of bounded variation is a difference of two increasing functions.
Oh, you assume that. Right. Oh, wait, you're doing the.
I'm using the previous lemma,
Right.
that f of x minus f of a is equal to the positive variation minus the negative variation.
Yes.
These are both increasing functions. I guess I don't have to show that they're increasing. It's obvious that they're increasing.
Yeah.
You just break the partition
Add a chunk.
and then add a chunk that's
Now,
non-negative.
The total variation, I think like a page up or something.
Yes? The total variation will be the sum of these two.
No, how was it defined originally?
Originally, it's the sum over any partition. It's the soup over all partitions.
Right.
You sum the absolute values
Of the variation.
of the variation.
Right, so in terms of P, F, and NF, it's exactly what the.
It's the sum of PF and NF.
Yeah. Yeah, okay.
Yep. So if that's finite, then each of these is finite, meaning bounded. And so that's it. Okay. Good. So yeah, I guess I can say if f is complex valued, you can do this for real parts and imaginary parts separately. What is it?
Oh, nothing. You just asking for small detail.
But other people could benefit from
The
the small detail.
F2 has no FA there.
Well, you have to stick it on one of them.
Right,
You could stick a negative
yes.
FA there or something because you're going to subtract it. But
Yeah.
yeah, the point is so the difference of these two functions is f of x minus fa.
Okay.
So I just want to give that constant. I just want to put the constant somewhere.
Right, right.
Okay. Is this decomposition unique?
Up to the constant that you just, well, at least up to the constant that you just decided to put in the.
Well, I could take any stupid function that's increasing and add it to both of them,
Okay, that's even better.
right? So it's very much not
Very
unique. Okay. Good. Where are we? Right, I wanted to make this remark, maybe here, remark, if f is complex valued, you can still prove this, just do real part and imaginary part. So a complex valued function is its real part is the difference of two increasing functions. Its imaginary part is the difference of two increasing functions. If it's a bounded variation. Okay. Good. Let's prove the continuity.
Wait, is that the only way you can break uniqueness, by adding increasing function?
In a sense, yes, because if I have two increasing functions and two other increasing functions
Right.
that add up to the same thing, then change the differences around. So you have f1 minus f1 prime
Yes.
is equal to f2 prime minus f2.
Right.
So just call that some function,
Hmm.
and that's the function that you added to f1 and f2.
So in special cases, f1 minus f1 prime might not be increasing, but
That's right. That's right. So it doesn't have to. If both of these are somehow increasing, although these are nice because they will be. So this choice is kind of the nicest because wherever this function is increasing, this one's not. So it really is like a Jordan, singular decomposition. But I haven't imposed any such condition on these two functions. Okay. That we proved. Let's prove a theorem. Okay, so this is interesting. This is fun. Theorem. So let gamma be a curve. Well, as you said, it could go into any metric space. Or any metric space. But let's just stay with R2 or RD or whatever. If we have a curve, since I want to draw it in the plane, let's make it R3, and then I'll draw it in space. Is that slightly more interesting? Can you even see what this is? It's supposed to be a curve in R3. Okay, gamma. Anyway, it's true for any metric space. If it's continuous, so it's a curve, let B be a continuous curve of bounded variation, then this total variation function is continuous. Okay, so the total variation function can't jump very much. All right, let's prove the left continuity. I mean, it's kind of, let me give you a sketch, because it's kind of clear what to do. Maybe. Sketch. Well, what do? Okay, let me revert back to R2, or better yet, R1. So here's my curve. Here's a graph of the curve. And I have some partition. So here's some point X. Here's A and B. Okay, and I've computed some total variation. And then I want to look at the total variation just after X. Okay, so the total variation, I mean, it's kind of clear what you do. You take any partition of X plus H, and you just make sure that there's an element, because of the continuity of gamma, you make sure that one of the partitions includes this point X. And then this difference will be at most epsilon by the continuity of the curve. And so this recovers the partition from A to X. This is the partition from A to X plus H. That's a refinement. Yeah, refine it if need be. And you're done. And this is the continuity in the right direction. You can do the same thing in the left direction. Maybe let's not spend time on it if it's clear to all what's going on. So take partition. I'll just write a few words. Partition of A to X plus H, which will have value, which will have with, what did I call this? The variation of f on this interval. relative to this partition. What do I call this? Variance of
The P.
of the partition with this within epsilon of the variation TF on a x plus h. And if necessary, refine the partition to include a point x, which is so that h is small enough. For h small enough, f of x minus f of x plus h is less than epsilon, or I should say z, if z is the thing that this curve is parametrized by. I guess I'm calling this z of t, although I could call it f of t. Somehow, there are standard notations bothering each other. And if needed, refine partition. If needed, refine partition to include x. Dot, dot, dot. Okay? So the partition, the point is the limit of TFA x plus h as h goes to 0 is TFA x.
So this is right continuity?
This is right continuity, and then you do the same exact thing with a minus h for left continuity. You don't need me to waste time on filling out the details.
I just feel like it would just be tedious.
It's tedious. Good? Okay. Good. So now we can really try to make progress towards the main theorem of the day, although even that we might not make. So, is that even right? Okay, close enough. So, okay, so let me state the main theorem. I guess I already stated it. I'll state it again. Main theorem of this section that we're headed towards. So if f is a function from a, b to r of bounded variation, then f prime exists almost everywhere. Lebesgue almost everywhere. Okay. I should have said, I'm trying to again explain why Lebesgue measure is the right thing. Right? One of the things that Lebesgue measure is supposed to do, well, there's a bunch of things. One, it's supposed to make Fourier series. It's supposed to explain which Fourier series converge and don't converge. Which functions are integrable? Well, the Riemann integrable functions certainly are, but there are limits of Riemann integrable functions that are not Riemann integrable. But L1 is a complete space. Here's another problem that it solves. Which integrals are antiderivatives, or I forget how Lebesgue phrased it in some funny way of saying, when does f prime exist? And if it exists, then we can integrate it and get f of b minus f of a. Right?
In particular, is established for increasing functions.
That's right. So we will do this because of the lemma. We can do this for increasing functions. So proof takes several steps. The proof is not at all obvious. Proof will start with continuous functions. Let's look at continuous functions. And work our way towards general functions, and then can use increasing by the lemma that any bounded variation function is just the difference of two increasing.
So from now on, we're just going to work with an increasing function, because if you establish it for one, then you just establish it.
Yes, although the next thing I want to prove, I don't want to assume the function is increasing, but I do want to assume it's continuous.
So
But
so we drop continuity in the second part?
we're going to slowly drop continuity and work our way up to the generality of this statement.
Okay.
So bounded variation is not at all requiring continuity, right? We can have jump discontinuities. In fact, those are the kind of the only discontinuities of a bounded variation function. And then we'll get to still just integrals with respect to these. Okay, let's go. So what I want to prove is the sunrise, the rising sun lemma, which is a fun name for a very simple thing. So let's call this lemma. This is due to Riesz, often called the sunrise. I'll explain what it says.
Oh my god, does
So,
it have to do with people mispronouncing his name?
no.
Oh. Riesz.
Rise, no. No, although, yeah. I guess it could.
Like rise the right way though?
I thought it was race.
But it's EI.
It's IE.
That says EI.
Oh,
Well,
So who's wrong?
It's not German.
It's IE.
It's not German. It's
is it
Hungarian.
IE? Do I misspell this all the time?
No, in
It
China
is
we-
IE, it's not German, but
Had
it,
it wrong.
It's Riesz.
Get rid of it.
But it is pronounced.
It's definitely Riesz, but I guess it's IE.
Which
Have I-
race is this? The better one.
There are two
Oh,
siblings.
The bigger
Yeah,
one.
it's this. All of the theorems, as far as I know, are from the one and not the.
The
The
big
free
one.
cash.
Yeah.
Marcel.
Okay, here's the statement.
Sorry, Marcel.
So let's say you have a function from AB to the reals, and it's continuous. So let's take a set E, which is a set of x in this interval, although in a second I'm going to say something else, for which there exists an h, which can depend on x, positive, with g of x plus h strictly bigger than g of x. So now I can explain why this is called the sunrise lemma.
So it's like H sub X.
H, yes. So there's some point in the future, which so let's look at g. G is some continuous function, right? Here's g. This is g. This is a. This is b. Okay. Which point does this point have a point in the future that rises above it? Yes, because this point has a higher g value. Okay, so this is in our set. All of these guys are in our set. These guys all have a higher g value. How about this guy?
No.
There's nobody in the future that has a value as high as him, so he's not in the set.
Near the end, nobody does.
Near the end, nobody does. So maybe this is the last point. So this is in E. This interval is in E, and this to here, this interval is in E. Okay, so this is E,
And the whole left, right?
and this is in E. So what you think of is you think of the sun rising early in the morning. This is east, and the places that are shady are E.
It's really nice. It's
Well,
really
it depends on the angle, this like how early you do it, right?
perfectly.
The sun is infinitely far away, and so its rays are all parallel, and they're coming from the
Good
east.
physics.
This is east. I guess this way is north? No. This way is up out of the earth. Okay? This E is not to be, this is east. Not to confuse with that E. All right? So there's a set. The book gets a bunch of things wrong about this, incidentally. So I do not want to include the point A in my set E, because I'm about to say the following. Then, so that's this set E. Then, what do I want to conclude? First of all, well, E might be empty. So if it's strictly if the function is strictly decreasing or just decreasing, then if E is not empty, E is open. And moreover, since it's an open subset of the real line, we know the structure of open sets. E is a disjoint union, countable disjoint union of some intervals, which is what we saw here. And G of Bj is equal to G of Aj.
What's BJ and AJ?
So these are the endpoints.
Oh, yeah, sorry.
Whenever you have these intervals, the value of G here and here is the same, except if Aj is equal to A. Because there might be some initial thing that for which that's not true. So these are two things that the book gets wrong.
So what two things does the book get wrong?
Well, they're not careful about A possibly being lower.
And then the other thing they get wrong?
I'll say in a second. So they're kind of related. They include A in this set. Now there are people that include A in this set, and then they have to say more about either if they're open except at the end. It might be half open. So I'd rather just say it's open, and then anyway.
Can you say open relative to?
It's relative
space?
open. Yeah. Relative open means it's the intersection with an open set of the restriction
But
too.
even if you included A, that still wouldn't work. Because like if you had like, oh.
So if the relative open means you take this closed interval and anything that's the intersection of an open set with my closed interval. So
Yeah.
that'll allow this closed at the end.
Yeah.
So relative open. Okay, that's what we want to prove. It seems kind of clear. I mean, the picture just kind of does it, but that's not a proof. And in fact, I don't know, maybe you guys are happy with this. The book just says the openness is obvious. And I don't think it's obvious at all. I mean, okay, the condition, let's look at the condition. It's kind of an open looking condition.
Yeah, if you're continuous, it seems obvious, sure.
Yeah, how do you prove it?
Think about it.
How do we prove obvious?
Yeah. So let's prove that it's open. I think this deserves proof.
Can we do like an in-class exercise where we think about it for 2 minutes?
Sure.
Does E really need to be non-empty? Isn't everything also true if E were empty?
If E is empty, then the rest of what I have to say here is vacuous, yes. This joint union is empty.
Yes.
Wait, so while people are doing the 2-minute thing, can you explain what E means again? Like,
What E means again?
yeah.
Yeah.
So,
I think I have it.
Okay.
2 minutes is over.
Not yet, yeah. So E, I look at all the points X. So here's point X. Here I am. Is there some point in the future that gets strictly larger than my G value? So I'm here. Is there somebody later that gets bigger? Yes. So I'm included in E. How about here? As far out as I go to B, I can see the sun, and so I'm not in E.
So any mass is,
Oh, if we can find one point, can we like find a neighborhood around that point and see like?
That's what I want to
Okay.
do, yeah.
All right.
Given a point, so a forward neighborhood is easy to find. Forward neighborhood is obvious. How about a backwards neighborhood?
Ooh, that's not so obvious. No, that's still fine, because you're continuous. It's like you can get arbitrarily close to the value, so you make sure that you're closer than the difference of the point that's further up, right?
So how
Yeah.
about we fix h for any h,
Yes?
and notice that g of x plus h minus g of x is a continuous function.
Yes?
So the inverse image of the positives under that continuous function is an open set.
I like that.
And then take the union over all h.
I like that. I think that does it. Let me give you my argument because it has a claim in it, which will then help prove the rest of the lemma. So here's the argument. All right, let me say it like this. That also works. So that this difference for positive h's is continuous, and then you use the continuity to show that its inverse image is open. Okay, so if x is in E, then there's some future point that rises above it. Well, that means that if you go just a little bit, if you go between x and that point, that also, so So there exists some point after it such that g of x plus h is strictly bigger than g. That's what it means to be an E. So by the intermediate value theorem, if you like, so g is continuous, g continuous implies by the intermediate value theorem that if you have another y between there, how do I want to say this? Well, there exists, let's just say, there exists an interval x, x plus epsilon contained in E. Okay, now let's extend that interval as far as possible. Extend as far as possible. Extend epsilon, right? Extend epsilon as far as possible.
Take the union over all epsilon.
The union of all of the epsilons for which this thing is in E. So then I get a set, let's call it x to x plus d, which is in E. And now if d were in E, then I can still extend farther. Because I just said anytime I have a point, I can extend farther to the right. So that means d is not an E. And d itself is not an E. So that's what it means as far as possible. If d were an E, then I could extend that even a little farther. Okay? My claim is that
D is not any, or D is
Yeah,
not-
x plus.
sorry, x plus let's make this d. X to d. Okay? So I'm extending this x plus epsilon out to some point d. And my claim is that g of d is strictly larger than g of x. This will be useful for the proof. Why does this imply that we now also have left continuity? This implies x minus epsilon to x is also in E. Well, I have this interval, and I know that on this interval I rise by some amount, and so there's a neighborhood of x that rises by less than half of that amount by continuity, and that neighborhood goes to the left. So all of these guys have to be in E because there's a value that's twice as far from their values as to g of x. Okay? So if I can prove this claim, then that implies the openness of E. But the claim is actually more important than the openness, which you can prove by other means. Okay, so let's prove the claim. Well, let's assume the contrary. So if, by contradiction, g of d is less than or equal to g of x.
Why? Well, sorry. Why does there exist why is it how are we applying the intermediate value theorem to get an entire interval x plus e?
So I'm not applying the intermediate value theorem to get an entire interval. I'm just applying the intermediate value theorem to get some interval. So there's a point in the future
That is like greater.
that is greater. Yeah, let's draw a little. It's very hard to draw subtle pictures with this marker. So here's x. I know that there's some future point h that gets higher. Okay, so I don't know what's going on in between, but somehow I'm continuous and I get to some higher value than the value I was at. Well, that means that any value in between, any value a little bit to the right, well, it can't go up by more than half of this amount. I can fix some interval that goes up by no more than half that amount, and I hit all the intervals in between, or something. I mean, I could just use, I don't even need the intermediate value, just use continuity,
Continuity doesn't go.
that it doesn't go above,
Yeah.
above whatever this was.
Is d like the inf of all h such that?
Well, that h could be far in the future. There could be other, all I know here is that there exists some h, but that doesn't have to be the right h. Like if I'm, let's say this is x, So this could be an H, but this could also be an H. Whereas this is the right D.
So D in this picture is H, it's not like.
Well, this is a,
epsilon.
in this picture, well, any of these could be, yeah, D in this picture is H, that's right.
Okay, so D.
But
is-
H could also be here, or X plus H, whatever.
So like Charlie said, D is something like the input over all possible H?
I think that was wrong. I was thinking of something else.
Yeah.
Okay.
Yeah.
So what were we using the intermediate value theorem for?
We're not. You want to call this continuity?
Yeah.
Continuity. Just use the continuity.
Okay,
Okay. All I was trying to say was, well, I'm going to hit every value in between.
yeah.
And so, in particular, I don't even need to say that. Look, there's a, by continuity, there's an interval around this which grows no higher than half of this. So all of those points will get
Yes.
no more than halfway up there.
Mm.
Good. Okay, so here's my x to d now. Maybe this is d. This is now d, and maybe this was some h that was farther out in the future. So I want to know that when I take this largest possible interval, the value is strictly larger than the value of x. So when we saw those humps, it's important that the endpoints here are not this largest endpoint, wherever this is. It's not in the set E. That's what I'm trying to. So what I'm trying to show is this value is strictly larger than the values that precede it. So if I flatline here, then this is the value that I stop the set E on. Does that make sense? Because this is a strict inequality. Okay. So let's see what happens if, so I'm trying to prove this claim. Let's leave the claim there. It's important. So my claim is that g of d is strictly larger than g of x. If by contradiction g of d is actually less than or equal to g of x, then let's see what happens. Then let's look at g restricted to x to d. So that's just this part of the curve. Well, d is not bigger than x, so it achieves its maximum somewhere. This is a compact interval, achieves maximum at, let's say, I don't know, z in x to d. Could be, I mean, if x could be the biggest thing a priori, but achieves some maximum value. And what does that mean? But z is in E, this is contained in E, which is still okay. There could be some much later value of g that rises above z. That doesn't bother me. So it achieves this maximum value here, but it's still in E. So, and there exists some y, which is it's greater than z, but it's at most b, which is the other endpoint of when we stop, with g of y strictly larger than g of z, because that's what it means to be in E. Again, let's parse this. If it doesn't achieve the maximum, if g of d is not bigger than g of x, well then look at this g restricted to this continuous function on a compact interval, has a maximum. That maximum is some point. I assume that point is not d, but z is in E, so that means there's some future point that gets even higher than z.
In fact, it's after d.
In fact, it's after d. In fact, it's higher than d.
Higher than, and occurs after on the line.
And it occurs after, that's right. It occurs, this y occurs after d. Except that, look at what we just proved.
So where is this b stuff? This y belongs to z and d.
So let me draw a picture. Let me draw a big picture. Let me draw a big picture and have you be able to see it too. I want the claim there too. Good. Okay, so here's a picture. Good. Let's do a couple of these. Okay, so here's my point x. I've gone out as far as I can to be increasing. Here's the point d. But let's say that the value of d wasn't larger. So somehow think of this as at the same height as x, at worst. On this interval, there's some value that is the maximum. Z is the maximum. But z is in E. So what that means is there is some future value that rises above z. Sorry. There is some future value that rises above z because z is in E. But if there's a value that rises above z and the value at z is bigger than the value at d because z is the maximum, that means d is in E. But that contradicts the fact that we went as far as possible by the right continuity of E.
Can you explain again why D can't be in E?
Yeah, what do we mean by as far as possible exactly?
So what we saw immediately was that the continuity, let's come back here. What we saw immediately was that the continuity of G told us that we had something to the right. So E is definitely right continuous, right open. For any value of x, there's a neighborhood to the right of x,
Yes.
which is contained entirely in E.
Yes. And D is like the soup of all D where you can form this interval. or
Yes.
something Like that.
So
Okay.
if D is in E,
Yeah.
but E is right continuous, then you could have gone a little farther.
Yes.
So you can't go any farther, that means D can't be in E.
So this E is right continuous. It's kind of a statement of being open in the topology generated by these half open.
By half opens. But in fact, it's also open in the traditional open sense.
Yeah.
By this argument or by other arguments. Okay? Does that make sense? So when you make these intervals, you have to wind up with a value of G that's strictly larger than the previous value. And now we're basically done. Okay, so this is a contradiction because D is not in E. This is a contradiction because D is not in E. So we have this claim. Everybody can see that. So let me slide it over here. So once we have this claim, so we know that E is open. So E is open, proved that E is open. So E is, we know that E is this disjoint union of intervals, AJ, BJ. So from X we go far to hit the next D, which is one of the BJs, and we can go backwards and hit the smallest thing we can, except for that first interval, which might be half open. So what do we want to know? So claim is that X in one of these AJ, BJs has its value strictly less than the G value. That's exactly what we just proved. Okay? Claim, what I mean is the claim implies, this claim shows you that anytime you're in one of these values, G of X is strictly less than G of B.
Because you could, otherwise you could have made the interval bigger or something like that?
Well, just what does this say? It says that if you've gone out as far as you can, then that value, the G value, when you've gone out as far as you can, is strictly larger. So this is in the interval. In other words, X to BJ is one of these X to D intervals, and the value at D is strictly larger than the value of G. Okay? But G is continuous. G is continuous. So that implies I can follow this all the way down to AJ. This is true for any X in the interval. So it's true in the limit, but in the limit, all I can say is AJ is less than or equal to G of B, B of BJ. It might approach. Okay? On the other hand,
In the limit
X goes to AJ.
as X,
Goes
yeah,
to AJ.
I take the limit as X goes to AJ. So take x to aj, I guess from above. X is coming down to aj. Okay? But, again, aj is not itself in E. But aj is not in E. Well, if aj isn't A, if we're not at that first endpoint, where we might be.
Well, AJ still wouldn't be an E because we excluded it from
We
A.
excluded E, yes.
Never mind.
But what I'm about to say won't be true if aj is A. So what does that mean? If it's not an E, then there is no future value. So there does not exist a future value such as bj with g of aj being, with this g of bj being strictly larger.
Means they have to be equal?
In other words, they're equal, which is what we wanted to prove, which implies g of aj is equal to g of bj.
Can we say again briefly what's the problem with A? Like, why doesn't this work if AJ is A?
Well, just because aj could be in E if we don't restrict E not to include A.
And there you're just using openness, right? Like if you have a open interval, it can't be in the set E if it's open in the left.
Yes, but so there's the E, which is the definition, but I can't use the definition at the point A because I've excluded the point A for a different reason than that it doesn't satisfy the definition. It could satisfy the definition, and I'm excluding it for just because I don't want it there. To say that E is open. I could say E is relatively open, and then, well, it's still not true that this conclusion of the endpoints being equal. See, what we proved is that the endpoints are equal. The G values at the endpoints are
Yeah,
equal.
so what's the picture where that's not true for A? I guess right there, actually. Come to think of it. Okay.
Okay.
And what was the claim we were trying to prove? Like what was the theorem?
Here's the lemma. So if G is a continuous function from A to B, you let E be this sunrise set. This is the sunrise set. Okay. Then this set is open. And being open, it's the disjoint union of countably many intervals.
And at the end-
And the G values agree at those endpoints, except for the first one.
Yeah.
And nothing bad can happen at the last one.
Nothing bad can happen at the last one because it just stops. There is no future value. So it's not an E vacuously. G is not defined.